Inside this fortress, the defenders face a desperate internal crisis. Their well has run dry, leaving them entirely vulnerable despite the strength of their walls. This highlights a strategic paradox. To successfully repel an attacking army, a stronghold must occupy the highest, most rugged ground available. But that elevation physically isolates the inhabitants from reliable groundwater. They are left dependent on seasonal rainfall or the slow, manual transport of water from the distant valley floor. Without a continuous supply of water, even the most heavily fortified castle will fall within days. To survive, they have to move a heavy fluid across miles of chaotic, uneven terrain. Lasting security for these soldiers requires a mastery of gravity and a total re-engineering of the surrounding geography. The first hurdle is capturing a reliable source. Workers begin a massive excavation to catch mountain runoff. Success depends on a precise, gentle downward gradient. Finally, stone masonry creates a permanent, controlled path, safely guiding the water. This technique allowed ancient builders to transport water over vast distances through relatively flat terrain, as seen in these surviving stone irrigation channels. But capturing the source is only the beginning. The real engineering test occurs when the landscape drops away entirely. Eventually, the water's steady downward path is interrupted by a deep, expansive river valley. If the flow follows the natural slope into the gorge, it pools at the bottom. It cannot climb the opposite side to reach the fort without an external source of energy. To maintain the necessary elevation, engineers construct aqueduct bridges. These structures carry the water across the void while preserving the exact downward gradient required for a continuous flow. These massive, multi-tiered stone archways were built on a staggering scale, all to protect a stream of water only a few feet wide. In effect, the aqueduct acts as artificial geography, a man-made landmass designed to keep the water moving across a gap it could never naturally cross. Once the water reaches the base of the fort's hill, it faces its final obstacle. Here, gravity is no longer an ally helping the flow, it is a weight pulling it back down the slope. Because the water cannot flow up the incline naturally, engineers must harvest energy from a faster, lower stream to power a mechanical lift. A water wheel placed in the lower stream converts kinetic energy into mechanical power. This rotation drives a chain of buckets that physically scoops the water and carries it up the ramp. Ancient engineers anchored these massive wooden engines directly into stone architecture, creating a permanent mechanical advantage over the steep terrain. This conversion of natural energy into lifting power effectively neutralized the defensive benefit of the fort's steep incline. The process concludes as the lifted water flows into the final trough and pours directly into the heart of the fortress. These circular stone basins became the centers of life in isolated settlements, providing a reliable reserve that defined the limits of where people could live. Securing this permanent water supply allows a dry, vulnerable outpost to support a consistent population and survive the pressures of a long-term siege. Ultimately, the endurance and expansion of human civilization is a record of our capacity to reshape geography to our own design.